now I'm going to discuss the radioactivity, and I am going to simulate this using the idea of random numbers. So first of all, let me talk about that. What is radioactivity? So it's a spontaneous decay. Radioactive nuclei. It's a spontaneous decay of radioactive nuclei. If we are having a sample and the sample is radioactive, then out of which sample, which nuclei will decay? It is a random process. So how this actually happens? It depends upon that how much nuclei we are having in the beginning, and with the passage of time, few of them will nuclei will decay and others will not. And the whole of the process is a random process. So that means random numbers may help us to understand this phenomena. So in this lecture, I am going to talk about that how random number help us to simulate this idea. So let us proceed as follows. So let we are having a number of nuclei at t is equal to 0, means initially we are having a number of nuclei, and sometimes we may call it as n0, but let me call it as n, right? So n is the number of nuclei, and we are having a radioactive sample. Now, in a small interval of time dt, dn number of nuclei will disintegrate. So now, this rate of decay or this decrease in the number is proportional to the number of nuclei at that time, and also depends upon the time during which those nuclei will disintegrate. So that means we can say mathematically that it is minus lambda dt. And sometimes what we do to do this, what we will do, and here we will use the concept that t is equal to 0. N is the number of nuclei at any time t, but at time t is equal to 0, let me call it as n is equal to n naught. If I use this concept and integrate it, then n means the number of nuclei at any time t is equal to n naught exponential of lambda t. This is the equation which we are getting. That means the nuclei, if we plot, this is time axis and this is n axis, then say initially this number is n naught, then the graph is exponentially decaying graph, which we are getting from here, right? That's what we are getting. So as I suggested, that the decrease in the number is basically a random process, or the decay, this is a random process. So that means to model this, I will use the concept of random number. So to do that, let us proceed as follows. Now, modeling of this, how to model this problem, let us have a look at that. So to model radioactive decay, let us imagine NT is radioactive nuclei, is the number of radioactive nuclei at time t, and let delta n be number of particles that decay in time decay in small interval of time delta t. So that means delta n upon n is basically, and delta n is a function of time, and this n is also function of time. That means this is the number of particles decayed in time delta t, decayed in time delta t. This is very small time in which number of particles decayed, and it is the number of particles at time t. And if I try to look at it, then this is a number always less than 1, and this is equivalent to probability. This is equivalent to probability. But as we know that this dn is equal to minus lambda n dt. So keeping this in mind, we can say that delta n upon n, it can be written as lambda delta t, or I can say that this is delta n over n, delta t is equal to minus lambda. So that means the number which we are getting, this number is equivalent to probability. This suggests that this equation suggests that probability of any one particle decaying per unit time is constant. So that means we are having a constant probability, and it is depending upon the decay constant. Right. So this is a very important concept which we have to keep in mind. So that means here two events are occurring simultaneously. Here two events are happening simultaneously. There is event A and another event is event B. Let me describe that. What is event A and what is event B? So a nuclei decay with probability P, and this P is equivalent to decay constant, and another is a nuclei does not decay with probability one minus p, right? That's what will happen. So let us now define the decay probability as that p is equal to delta n over n naught. So n naught is what? N naught is number of nuclei in the beginning, means at t is equal to 0 in the given sample. Now what I will do, I will relate this probability with the random number. And let us call this p as the probability and x is the random number. So that means if probability is less than x and if probability greater than x, if it is this, then nuclei will decay and otherwise nuclei will not decay. And here nuclei will not decay these are the two things which are happening and we are relating it with the random number. And if there is a decay, that means number of nuclei will decrease. Means there is a decrement in number, decrement in the sample. Means this thing will leads to the decrement in the sample, right? And with the passage of time, for different time steps, we will keep on doing this, and with time we will try to plot this number of the parent nuclei with time, and we will get a graph like this, right? So to understand this, let us do one thing, that I will use the concept of probability, I will use the concept of random numbers, and for that let us proceed as follows. I have chosen different random numbers which I am getting between 0 and 1. I have chosen 100 random numbers. I have chosen these random numbers from some program used to generate random numbers. So we are having, these are the random numbers. So, and let us call that probability of decay will be 0.2, which I am choosing in this experiment. So here R6, here it is less than 0.2, less than equal to, if it is less than equal to 0.2, and if it is greater than 2, then nuclei will not decay. So that means for first random number, there is no decay. For second, there is no decay, there is no decay, no decay, no decay. But corresponding to this random number, there is a decay in the nuclei, and so on. Here it is decaying, and so on. Means the random numbers which are marked with the red boxes, that means corresponding to that there is a decay, and but for the rest there is no decay, right? So if I make a record of this and do a little calculation, I did this calculation here now. So this is the random number corresponding to which the decay will occur, right? So these are the different random numbers corresponding to which decay will occur. So initially 99, initially 100 nuclei are there, parent nuclei. Let us assume, I have assumed that parent nuclei are 100, and at t is equal to 0, daughter nuclei will be 0. So corresponding to R6, a nuclei will disintegrate and 99 will remain there, and here one daughter nuclei will be there, and so on. I have made this record. Now my next objective is to relate these numbers with the time. So I have taken, or I have incorporated the concept of time with the help of this half-life period and average life. So half-life is 3.4. Using this formula I can calculate. Lambda is corresponding to probability. So here I got the idea of this time. Half-life is this, so means after 3.4657 seconds, only 50% nuclei will be there, and after next time only 25 nuclei are there. So that means after first half life 50 nuclei are there, corresponding to this time will be this. And if I again taken half of this, means 25 nuclei are there, and corresponding to this the time is 1.73 roundabout. And for the next I keep on doing this and arrived at the number here. I keep on dividing time half-life with 1, 2, and corresponding to which means I keep on dividing the number of particles by 2, and then keep on dividing the half-life by 2, and so on. And I'm arriving at roughly here 1.5, and here it is roughly 0.105 seconds. So this is the estimate of the time, and this is the estimate of the number of particles. So if I did this, and then keeping these statistics in mind, what I did, I have again made a plot. This is the time and the number of parent nuclei. So it's just an approximation. These are not the exact figures. So at t is equal to 0, 100 parent nuclei are there, and after 0.105 seconds, roughly, it's a rough estimate, 98 nuclei will be there, and after 0.2166 seconds, 97 nuclei are there, and after that there is 0.433. It is this number of nuclei, and after this 89 nuclei are present. And I have got this from this, right? This is just a simple comparison with the time which I got from here. This time, yeah, if I try to look at this now, these are the various time steps. This is the one time step, this is another, and this is basically a simple approximation. They are not the exact figure. And if I try to plot it, that means it keep on decreasing. It's like exponential decay. If I do more calculation, but it's hard to do manually. So to appreciate it, what I did, I have written a Fortran code. Let me go to there. Let me share with you that program. So here I have written a program in the Fortran. Just see it. It is the n naught initial number of nuclei, daughter nuclei, and this is the decay probability p, and it is the maximum time up to which I want to calculate and it's a time interval, and this is the dt is the time interval, and here I am relating with the number of parent nuclei after that time interval, and this is relating to t average. T average means average time, and average time is 1 upon p, means 1 upon probability, right? So I use this concept, and finally I have calculated the theoretical value, means I have used the exponential function here to calculate the theoretical value, and I compared these results, and this is t and this is n, and it is a theoretical value. So if I run the program, this simple code, then these are the inputs which I have given. It is the initial number of parent nuclei will be 1000, and number of daughter nuclei will be 0, and probability is 0.2, and maximum time I have chosen 20 seconds. That what happens to the daughter nuclei after and number of interval is, this is the maximum time, right? So that means after 1 second, out of 1000 nuclei, 800 nuclei will be remained, but theoretically it is 819, and so on, 640 and 670 and so on. That's what will happen, right? So these numbers are approximately matching, and if we plot time versus these two, then we are getting a very interesting graph, which I want to share with you. Let me go to here. Yeah, the Fortran code, and let us have a look at the graph which I am getting. So this is nt and this is time axis. So using random number I am getting this graph, and using that theoretical equation means when I plotted the exponential graph, so I am getting this one. So both are almost matching. So that means using random numbers we can simulate the radioactive decay. So this is a very interesting application of random numbers to understand the concept of radioactive decay. Otherwise, it's a very hard concept to visualize. So that's all for this lecture.